was it? Negative 2 to the 2k over 3 to the k. And there's lots of different ways we could go on this one, folks. So when you look at that series, what do you see? Can you pick out what kind of series it is just by looking at it? Can you think of a test that would be easy to use on it? And like I said, there's lots of different ways to proceed on this one. It is alternating. So one way to proceed would be the alternating series. But is it alternating? Let's actually check it out. Now, why would you say it's alternating, Matthew? You see that negative. You see that negative there, right? But let's be careful, because look at that exponent. Yeah, you're exactly right. Yep. You're exactly right. No, and that's fine. And that's part of the reason this example exists is, oh, I see a negative to a power, but when in doubt, write it out. If you start looking at, what these powers are going to be, if I can multiply today, that's actually always an even exponent. So in fact, it's actually not alternating. All right. But once again, that's a good first guess. So it's not alternating. What else does it look like? Does it, is it a P series? Is it a geometric series? So for P series, it's got to look like a constant over k to the p power. So the k has to be in the base here. So it's not in the base. But where is the k? Where is the k? Yeah, it's in the exponent, right? And it's in the exponent in both places. So wait a minute. If the k's are always in the exponent, and that means it's actually what kind of series? It's got to be geometric. You follow? So this is the kind of reasoning. So like when you see a problem on the quiz or the assignment or in the homework, this is the kind of thought process you got to go through, okay? It's just like techniques of integration. You might not know exactly how to start, but try something, and you got to think it through. And that's why, a lot of times coming up to this point, with the exception maybe of trig identities. You remember verifying trig identities back in the day. There was no real roadmap there. You knew where you had to start, you knew where you had to finish up, and then you had, a pocket full of identities and algebra skills to try to change one thing into the other. That's the same thing here. You got a list of tests. And here comes something, and you want to see which test is going to apply. So let's try the geometric series test. This is a good review of that. Because we reviewed P series, we reviewed divergence tests, we reviewed limit comparison tests, we reviewed alternating series tests. Now we're going to review geometric series, right? So to be a geometric series, I need to start off and figure out the AK plus 1. So the AK is the term as is. And to get AK plus 1, everywhere I see a K, I'm going to replace it with the quantity K plus 1. So I'd have negative 2 to the what power? All right. So then to prove it's geometric, I need to take the ratio AK plus 1 divided by AK. So AK plus 1 and remember, instead of dividing by the AK, I'm going to multiply by its reciprocal. And now I'm going to group together what goes together. Well, because we distribute the 2 through here, Nick. So the K goes in to K plus 1, and then it gets distributed. Yep, no problem. So now I got to use our properties of exponents here. And I'll put our answer here at the top so we don't lose our train of thought. So remember, when you divide exponents, what do you do with them? Yeah, they cancel out. Good. So these are going to cancel out, and I'll be left with negative 2 squared in the numerator. And then what's going to happen here? What's going to cancel over here then in the exponents? The k's will cancel, good, and I'll be left with just a 3 to the first in the denominator. And so this is R. We get a number 4/3. Okay. Now, what do we know about geometric series? When do geometric series converge? What has to be true about the R? The absolute value of R has to be less than 1. And that's not true here. So in this case, the absolute value of R is 4/3, and that's greater than 1. So boom, I know that this series does what? It diverges. And that's it. There's no bother checking absolute. Well, I mean, the series is actually all positive terms anyway, but it just flat out diverges. So we want to determine is it absolutely convergent, conditionally convergent, or divergent. And so we'll go for the gold first. If the series is absolutely convergent, then it's automatically convergent and we're done. Let's check out the series we get looking at the absolute value of the terms. So once again, the absolute value works well with division. And it works well with powers. And the absolute value of -1 is 1. 1 to any power is 1. And k starts at 1 and goes to infinity. So 3k minus 1 is always going to be positive. So we don't really need the absolute values down there. So we're looking at this series. So we got to see what's happening to this series. Is everybody okay on the algebra here? When you take those absolute values, what happens? They hit that -1 factor and make it +1. All right, so now we got this series to look at. And once again, once you take absolute values, you've now unlocked all of the tests we have up to this point. So let's think about it. Let's try the divergence test. Let's take the limit as k goes to infinity of 1 over 3k minus 1. And what's that limit going to be? That's going to be 0. So if the limit is 0, what does the divergence test tell us? Nope. It doesn't tell us. If the divergence test can only tell you if it diverges. And the only way you're going to know it diverges is if this limit is something besides 0. So we don't know anything from the divergence test. So if the limit is not 0, we know that series diverges. If the limit is 0, it may or may not diverge or converge. So divergence test doesn't work. We try geometric series. We're looking for exponential functions. None of those. What about p-series? Is this a p-series? No. But as k runs off to infinity, what does this look like? 1 over 3k minus 1 is going to look a lot like what? 1 over 3k, and that is a p-series. So what series or what test can we use if we don't have a p-series, but in the limit it looks like a p-series? And that's the key there, folks, in the limit. What test can we use? So it's not a p-series, but in the limit it looks like a p-series. So what test can I use here? Yeah, limit comparison. All right. So this series resembles k equals 1 to infinity, 1/3 over k. This is a p-series. What's the power of p here? What's the power on the k? 1. And what's important about the number 1 when it comes to p-series? What's that tell us? Yeah, it has to be greater than 1 to converge. This is less than or equal to 1, so that means that this series is going to do what? Diverge. Good. So we're all set for the limit comparison test. So we're going to take the limit as k goes to infinity. We take the terms of the series we don't know about, divided by the terms of the series we do know about. The old invert and multiply. And what do you get out of this limit? Not -1. So this looks like the numerator is 3k, and 3k is showing the denominator, so it should go off to what? Yep, so it's indeterminate, infinity over infinity. So we use the leading term test. 3k over 3k is what? So leading term on the top over leading term on the bottom. 3k over 3k is? It's not 0. It's 1. This will go to 1. And once again, if you're uncomfortable using the leading term theorem, you can pass this to a continuous variable and do 3x over 3x minus 1. You could L'Hopital it if you want to and get 3 over 3, but you'll get 1. And what's important about the number 1? For the limit comparison test, we want to have our limit be what kind of number? Positive and finite. Good. So this is a finite positive number. So that means that we guessed right. This our unknown series is going to behave like this divergent series, which means the unknown series is going to do what? So what conclusion can we draw? It's going to diverge. Okay, so the series we started with then, k equal 1 to infinity, when we looked at the absolute values, the absolute values diverge. All right, so that means it's definitely not absolutely convergent. Let's see if it's at least convergent. So now we have to look at the series as given to us. So what test can we use on this series as given to us? What kind of series do we have here, folks? It's alternating, yep, and we could check it out. When in doubt, write it out. When I plug in k equals 1, I'd have negative 1 squared over something. And then I have negative 1 cubed over something. And then negative 1 to the 4th over something. Anytime you have negative 1 to an even power, that's going to create what kind of term? Positive or negative? Positive, negative, positive, and so on. So we have an alternating series. So if we have an alternating series, we'll try the alternating series test. So for the alternating series test, we take the positive parts of the terms, and we already did this. So that's, even though the alternating, or even though the absolute convergence didn't work out for us, we can reuse some of that work. And what do I need to check about these this sequence? I need to check two things. I need to check that it's what? Decreasing. Is it decreasing? And why is it decreasing? Yeah, so you've got a constant numerator with an increasing denominator. So the answer is yes. The numerator is 1 and the denominator keeps increasing. So that tells me that it's decreasing, and it also tells me, that's right. We also know then that the limit as you go to infinity is 0. Boom. And that's all we need. We have an alternating series where the positive parts of the terms decrease to 0. So that means that the original series converges. Okay. So let's put these two things together. We have that the series itself converges. And we have the series of with the absolute values of the terms diverges. So what kind of series do we have here? What would we call this series? Is it absolutely convergent, conditionally convergent, or divergent? Conditionally convergent. Okay. So what's nice from kind of a teaching standpoint about conditionally convergent series is one problem can have you work through a couple different tests, and I can kind of tell, I know this is a lot. That's why we're taking our time. I mean, we're not going to, we're going to finish up early today, and we're not going to move ahead because this is kind of deep stuff. We're going to finish up what we have today, probably finish up early, and then tomorrow we're going to introduce the last two tests, or one of the last two tests. We'll finish that up Monday, and then next Tuesday is probably going to be a work day where you just sort of sit down and try to put all this stuff together, okay? Because it's kind of like techniques of integration, right? It's kind of like the first chapter we did. In the following sense, techniques of integration, you learn like a half a dozen new ways to attack integrals, but and that's kind of what's going on here. You've got half a dozen tests to try to analyze series. Although with the integrals, you kind of crank through and it was business as usual using formulas. Here, it's a little more esoteric. You have to look at the series, try to figure out what it matches, what it looks like, and you really have to focus on the kind of big ideas of convergence. And that's tough to do, especially over the summer.